Hello students, the final topic is rank of a matrix. This is not really an essential topic because we're going to cover rank of linear maps in the next chapter, but let's talk about it anyway. Let's begin with the concept of row space and column space. What do you mean by row space? Let's consider each row as a vector, and then let's consider a subspace of Rm generated by these row vectors. You see, each of these are m-dimensional, each of these are n-dimensional vectors. Yes, this is m by n. M vectors, each are coming from n-dimensional vectors, so this is wrong. Okay, each one has n real numbers, all right? Okay, and then the subspace generated by these m row vectors is called the row space. And then the dimension of this row space is called row rank. You can do the same thing for columns. For each columns like this. Now each column is m-dimensional because A11, A21, it goes to m real numbers. So these are subspaces of Rm. And how many are those? There are n of them. And then subspace generated by this A1, A2, A3, these column vectors, is called the column space. And the dimension of the column space is called column rank. The thing is, the column space and row space, column rank and row rank are the same. And that's what we want to prove here. Now, an intermediate step is this, elementary row operations. And elementary row operations do not change the row space or column space. So how about this one? Non-zero C, non-zero real number C is multiplied over there. And you see, this this row space after elementary row operation and the original are the same because, this AI can be expressed as 1 over C times this and vice versa. This is given by C times that. So every generator can be expressed here, and every generator there can be expressed by linear combination of the other. Same goes over here. We are changing these two, but if you use linear combination expression, they're just switching the order of addition, so they are the same. And then adding one row to the other, even only that may be a little bit worthy of consideration. Yeah, A1, immediate consequence, and then B, nothing to prove for B. And as for C, A1 plus AJ is a linear combination of A1 all the way up to AI and then AM because we just add those two. And then each AI can be written as that and then minus. So AI plus AJ and minus AJ, and then these two cancel out, we get AI. So it can be written as a linear combination of these. So every generator is a linear combination of one and vice versa. So we are talking about the same linear spaces, same subspaces. Exactly the same kind of proof goes over to elementary column operations and column spaces. So they preserve row spaces and column spaces, consequently row rank and column rank. Tedious, but it's easy to see. And finally, rank theorem. Row rank and column rank are the same. As a matter of fact, we can do better. Applying some elementary row operation and column operations, we can change every matrix into this kind of form. We can embed identity matrix on top left-hand side corner, and everything else is 0. How can we do that? The proof is inductive. Okay. Suppose that A is non-zero matrix expressed like this, and without loss of generality, we can assume A11 is non-zero. Otherwise, if it is 0, we can apply elementary row operations or column operations to switch some rows and columns to move any non-zero element over here, and then start from there. So no problem there. And then, assuming this is non-zero, we begin with elementary row operation or column operation, multiplying by 1 over A11, and make this one into 1. Okay, so entire row we multiply by 1 over A11. And then we apply appropriate elementary row operations to kill off A12, A31, all the way up to AM1. Multiply by AA1 and then subtract. Multiply by AA31, subtract. Multiply by AM1 and subtract, and so on. Yes, basically this operation. Then we can make just 1, 0, 0, 0 like that. And then we do exactly the same thing to elementary column operation. Multiply by B2 and then subtract, that'll kill off. Multiply B3 and kill off. Multiply Bn and subtract to kill off. And repeat. This is what we get. Same thing I just talked about. So what did you get? 1 and then O0, O0, and then we have the submatrix there. Here we're going to use the mathematical induction. So the lower rank, order, so lower size are assumed to be of this form. And then in the end, we got that. So we can embed square matrix here, the identity matrix here. Only those are non-trivial. Everything is all 0. So what's the dimension? In column dimension, we have number of rows here for this identity. And for rows, I said it wrong. For rows, number of rows here from blue part. And for columns, number of columns in this blue part, but that square matrix is identity matrix. We have R by R, identity matrix, and that is the common value. Column rank and row rank, they are the same. And that completes the proof. Row rank, column rank, they're the same, and eventually every matrix can be rewritten like this after some elementary row operations and elementary column operations. That completes the final topic, rank of a matrix, an optional topic.